in Koestler's theories, and we have done up to, let me check. We have done up to that part. Oh, so I was worried for no reason, eh? Let me see. We still have a lot. What I want us to do today, I want us to first, after the water leaves barrages and headworks, after the water leaves the diversion headworks, it goes to canals. Conveyance systems, it can be a pipe system or whatever, but most of the time you find that it goes to a canal. And we are supposed to do canals somewhere. Yes, we are supposed to do drainage, and in drainage we are supposed to do canals. So I want us to go directly today and look at canals. We'll look at drainage later. Before we come to the design of the irrigation systems. Of course, we will start with gravity systems, then come to sprinkler, then drip irrigation systems. Yeah. Design of pipe systems. I don't know whether I should give one, but I shall decide. I always leave that one undone because it is done elsewhere, like in design of water and wastewater systems. It is always done there. So today, I want us to look at canals. I want to look at canals so that then I can take a snip of what we have here so that we can know where we are. Surface irrigation tool. All right. With that, let me open the canals. What am I doing? So, like I've said, water, once it leaves the irrigation system, it has to go now to a conveyance system so that you can be able to transport that water from the source to the point where it is supposed to be used in an irrigation scheme. Most of the times you have the water being delivered in earthen canals. Mostly in irrigation systems, that water is transported in earthen canals. If they are not earthen canals, we have looked at hydraulics, flow of water in open channels, non-erodible open channels, whereby the normal equations of Manning's, Chesy, and so forth and so on are used. But now, what happens when your channel is erodible? So what today, if it is erodible, that is earthen canals, for example, constructed in alluvium soil, if it is erodible today, a section of a channel, let's say initially you have constructed a channel that has such kind of a cross section. So one day you find that one day you may have erosion on one side, or deposition, and then you have erosion on the other side of the channel, such that the following day you have a channel that looks, let's say something, totally different because of erosion and deposition. Why? Because you have constructed that channel in alluvium, so it is erodible. And depending on the conditions of flow, the slope discharge, which controls also velocity of flow, and also depending on the amount of silt in the water. Remember, like in rainy seasons, we have higher silt content in channels. You are going to have either deposition or erosion. So in this case, the channel is changing from day to day. Now my internet is, if I become too shaky, you'll tell me. I tried to sort it in the morning. That is why I was late. But if I become too shaky, you'll tell me. So the cross section one day is one thing, the following day it's different. The slope has changed, the wetted perimeter has changed. And so the formulas that we have learned before of calculating flow, for example, the Manning's equation in a non-erodible channels where the cross-section is constant, slope is constant, can no longer be used. Now, when that happens, that means those equations to begin with can no longer be used. Secondly, when that deposition erosion is happening, you can have so many undesirable conditions. For example, if you have deposition, you can have weeds growing on the channels, increasing resistance to flow of water, and you can greatly affect the efficiency of your systems. Now, most of the time, when you have canals, which are carrying water from reservoirs, in reservoirs, remember, the water first gets into a less speedy flow regime. There is some kind of quiescent conditions. So if the water was flowing in a very high velocity, then gets into quiescent conditions, then you may have settlement of the silt particles which are in the soil through Stokes' law or Newton's. There is a Newton's law of settlement, but we also have Stokes' law, so both can apply. So you can have settlement of discrete particles because of that reason. The kind of settling that we usually calculate when we are doing settlement basins. So the same kind of settlement can occur. And you find that in the case the water is coming then from a reservoir with comparatively less charge, the off-taking canal can be of low velocity. That if the off-taking canal is of low velocity, then the silt will deposit in the canal bed, resulting into siltation and subsequent loss of carrying capacity of the water. And you may have to do a lot of desilting of the canal and all that. If you have a very high velocity, then you are going to have squaring so that the water can achieve optimum silt charge. So here we are talking about water coming from a reservoir. If it has a low velocity, you are going to have the silt depositing. But if the velocity is very high, there is usually something we call optimum silt concentration, but it is not concentration, we call it silt charge. And according to theory, water has to have a certain optimum silt charge in order to prevent either deposition or erosion for a given water velocity. So in such a kind of a case, you are going to probably have erosion of the channel so that you can achieve the silt charge that is optimum and as under the increased high velocity flow. So whichever the case, whether it is deposition that is happening, whether it is erosion that is happening, both are not desirable. Both will lead to reduced efficiency. And when you're talking about irrigation and efficiency of water, it is not a small problem. It is not a small matter. It is very costly because when you are calculating irrigation efficiencies, probably you came across irrigation application efficiency, scheme efficiency, and so forth and so on. And imagine if you are talking about the efficiency of a system is 70%, it is 50%, because in some irrigation systems, that is the level of efficiency. So if you have to provide, let's say, 1,000 millimeters of water in a particular season, and that is very, very conservative. Normally, you are required to provide much more than that. So let's say you are to provide 1,000 millimeter divided by 100. Yeah, 1,000 is still, if you convert now that into a volume and you're thinking about a very large irrigation system that is in terms of hectares, 30% of 100 is 300 millimeters. Multiply by 10 and then multiply by your area in hectares, and imagine the volume of water that can be lost simply because of losses in distribution. So designing canals, because of that, designing canals becomes a very critical and critical aspect in irrigation. Now, we are going to look at first the background of general design of open channels, where it started, what we have in the literature, and how they came to be applicable in design of erodible channels. So first we start with design of artificial canals using empirical formula. And the Chesi formula is the oldest design equation for designing open channels which are non-erodible. When we say artificial canals, we are talking about non-erodible. And generally, it is of the format V velocity of flow, mean velocity of flow is equals to the Chesi's constant square root of mean hydraulic radius multiplied by the surface water slope. Most of the time, that surface water slope is equal to the bed slope of the channel. It is only not parallel when you have backwater effects. And most of the time, and backwater effects will happen if you have some kind of pondage ahead. If you have some pondage ahead of somewhere in the downstream, you are going to have backwater effects. So generally, when we say the water surface slope, most of the time we take it as the channel slope. When you look at this equation of Chesi, first in literature, it is assumed to be the basis of all formulas for calculating flow in open channels. And it is based on a number of assumptions that, one, we have, or rather the force that resists flow per unit area of the channel is proportional to the square mean of velocity, is proportional to the square mean of velocity, and that is why we have this root RS. C here is kind of the proportionality constant. And then secondly, For the water to flow in a downstream direction, the forces that resist water from flowing, and what resists this water from flowing, we have things like surface roughness of the channel should be counterbalanced by gravitational forces so that it can be able to move. And it has certain disadvantages because, one, it is recognized worldwide as a classical equation of flow, the oldest. So it is recognized and it is applicable in all cases where uniform flow is assumed or exists. But it has some limitations. One of them, when you look at this equation, velocity units are meters per second. The right-hand side, C, is a constant which is unitless. R, the unit is meters. S, the unit is unitless. So when you look at the units on the right-hand side, meters per second, on the right-hand side, the resulting unit is square root of a meter. So that equation is dimensionally inconsistent, or we can say it is dimensionally incorrect. And we have done dimensional analysis before, so this one is not dimensionally correct. Two, it does not take into account the physical character of the channel. Notice, first, what it says, some of the assumptions is that the effective component of gravity force causing the water to flow must be balanced by total force of resistance. Where does this resistance come from? It will come from the physical character of the channel, but Chesi formula does not take any cognizant of that kind of assumption. Thirdly, it is derived from a limited number of observations, but then it is applied in all types of channels. Roughness. Then for the assumption that the gradient runs parallel to energy gradient in a condition which is realized in fairly steady irregular channels in steady or nearly steady discharge rates. And I talked already about that slope, the slope that the water surface slope that we assume the water slope to be equal to the channel slope. But what this limitation says is that is based on an assumption of steady or nearly steady discharge rates. But does that happen always? Well, we know we can try to manage and control that by having canal head regulators, but are we going to have steady discharge? Then it is valid only for channel cross-section resembling wide rectangles with lovely level bottoms and parallel flow at right angles. We have now all other equations that we are going to look at still for designing artificial, canals using empirical formula. They're all based on the Chesi formula. We have Kuta's formula. And in Kuta's formula, of course, you start with the classical equation, that is the Chesi formula. But then Kuta has gone ahead to work on some of the limitations. And he defined C, a very complicated formula. And in C, he characterizes both the channel roughness by using the Kuta's roughness factor N, and also the water surface slope and relationship between water surface slope and mean hydraulic radius depth. We have from this Kuta's equation typical values of Kuta's N for different for channels or canals with different bed characteristics. For example, you have an alluvium regime, loose gravel, rock cut, smooth and regular, rock cut and irregular, and so forth and so on, and very various values of n based on whether the channel is perfect, good, fair, or bad. One thing you notice about calculating velocity of flow using this formula, and especially when you go to the field, there's a lot of subjective decision making. What is the definition of perfect, for example? What is the definition of good? What is the definition of fair? And what is the definition of bad? That is a question that you always have to answer. Even when you are doing the Manning's formula, those are the questions that you are supposed to answer when you are making a personal judgment call in the field. The types of N also are based on discharge in ordinary soil, and the values are given. And we have some limitations. One, it is unnecessarily complicated. Really, look at where we have started. Starting from V is equals to C root RS, and then someone adds C. TC becomes all this very, very complicated. Brian John Obumba, you got us joined with the call option, microphone option. I think we have agreed that before. Then we have the coefficient C rises with slope for values of R less than 1, but drops when the slopes rises as R are greater than 1. So that one rises from the way the formula configuration and the position of R, the position of R in the equation. So when R, what we are saying is C will become greater for values less than 1. What happens when you get a square root of R less than 1, you're going to get a very, very small value. And when R is greater than 1, the value is always going to be greater than 1. Then finally, N is assumed to depend on the nature of the channel material alone. Then we have Manning's formula. That one I know we have come across it many times, whereby now we still start from C is equals to square root of RS, but now the C is much simpler. And then we have introduction of Manning's roughness coefficient. And you can notice that these values of N, according to literature, we are told that these values of N are comparable with Kuta's N. If you have a trapezoidal section, the discharge through calculating discharge through a channel, non-erodible channel using Manning's equation can be simplified into this equation. We have some limitations. That is the exponent of R in relation to C is not constant but varies depending mainly upon the channel shape and roughness. So imagine R is the hydraulic radius, and it is supposed to be constant for a given cross-section. 2, and this one becomes, the limitation is because C in Chezy's formula is supposed to be constant, but if R is varying for a given channel, then that means C is also changing, is supposed to also change. But in Chezy's formula, the C is a constant. Mercy is making tea or something, eh? Then we have proper selection. The second limitation is that the proper selection of N to be used is a complex problem. and it depends largely on personal judgment. And I've talked about this. It's a very it may have seemed to be easy when we were doing hydraulics, but the complexity of it comes when now, because like now we are supposed to be applying these equations in design. When it comes now to design, you have to make personal judgment. It's not a fact. You know, it becomes as difficult as if you were doing some art thing whereby someone is asking you, how good do you think that person is? And whereby I will say, well, that person is not a good one. But another person says, that person, no, is good. Because on the way we, the beauty lies in the eyes of the beholder. Goodness will lie on the eyes of the beholder. So the personal judgment plays a very big role in selection of the value of n. We have Bayes' formula where R and C are related using this formula, and M, in this case, M is the Bayes' coefficient of roughness and depends on roughness of the channel, and typical values are given before. This Bayes' formula is derived from data collected from small experimental channels, and it is usually less satisfactory than both Kutter's and Manning's. We have Pavlovsky's, and Pavlovsky's, you could say it is just because it's more of a USSR equation. And we have two kind of sets of science principles or scientific regimes in the world. We have the Russian one, and we have the, we have the others. We have the Russian one and the others, and this one is just basically because it is Russian. If you go to and do Russian classes, maybe you'll encounter it quite more often. And in Pavlovsky's, C is defined as you can see. But now Pavlovsky's is only varied for values of hydraulic radius between 0.1 and 3.0 and n between 0.011 and 0.040. So these formulas we have discussed, you'll find that they have been used, and you will find them theoretically used in design of artificial channels, but they're limited because they have no, like I explained before, when you are transporting water with a certain silt concentration, you may have deposition or erosion based on the silt concentration, silt charge. And these formulas have no reference whatsoever into concentration of the silt in a channel. And what was seen in literature, and according to literature, the observation was all channels, inerodible channels designed using these four basic equations often resulted into heavy siltation requiring frequent silt clearance. And so the regime approach was adopted or was developed in order to be able to address such kind of a challenge. And we are going to look at two regime approaches. We have Kennedy's theory and Lacey's theory. We have Kennedy's theory and Lacey's theory. And we are going to start with Kennedy's, and Kennedy's theory is based on the assumption that as the water flows in a channel, assuming a cross-section as we have here, as the water flows in that channel, you are going to have, as the water flows, there is friction between the water and the surface of the channel, the bed of the channel, and you are going to have vertical eddy currents that keep silt in suspension. And according to Kennedy, all those eddies emanate from the bed only, of the channel. And they are responsible for keeping the silt agitated so that it does not settle. Remember, when we are designing this, we are trying to ensure that there is not going to be deposition. And when we talk about, and first let me just talk about a regime approach. A regime, these theories that I've talked about, both Kennedy's and Lacey's, try to design a channel that neither erodes nor experiences deposition of the silt. It's kind of an optimum channel cross-section and longitudinal slope, whereby once given a certain velocity of flow, you're not going to have deposition, you're not going to have erosion. So the channel and the water and, and the silt concentration, the channel cross-section, the channel slope, the channel geometry, the silt concentration and the velocity of flow are all in equilibrium. So the regime approach tries to get to design such kind of a channel. So the Kennedy's theory, in Kennedy's theory, he assumed that in order not to have deposition, you have these eddies emanating from the bottom of the channel. And he developed his first formula correlating mean velocity V, which we call Kennedy's mean velocity, in a regime canal with vertical depth D. Mercy, I muted you. You have unmuted. You have a question?
No, it's my connection, my network.
It's a connection. All right. I thought you were taking tea na sisi hatujakunywa bado.
Hapana.
Tutakunywa tukienda break.
Okay.
All right. So long as it does not bother people. So now, this first formula correlating mean velocity V in a regime canal with a vertical depth D can be estimated using this formula of, for calculating critical velocity V naught as C multiplied by D raised to power N, whereby D is depth of water and C is constant, while N is the index number. And in his very early calculations, the value of C, according to him was 0.55. Now, notice in this formula still, we do not have any form of reference to the silt, characteristics of the silt. And what he did, Kennedy's theory later, the equation was modified, and the critical velocity V naught, now, which we also call Kennedy's critical velocity, he introduced the parameter M, which is the critical velocity ratio, which is V, actual velocity of flow divided by critical velocity of flow, and it became a component of the design formula. So this one. And you notice it now takes a general form of V naught is equals to C, which is 0.55, M critical velocity ratio, then D 0.64. And so generally, or henceforth, Kennedy's formula, henceforth after this introduction of the critical velocity ratio, that is what is used. Now, when we are designing channels, when you're designing canals, we want to know the cross-section of the channel that is supposed to deliver a certain discharge, but we also need to determine the slope, that slope of that channel. So let us put that one in mind somewhere, someone in mind, because we are going to come back and talk a little bit about the slope and Kennedy's theory. Is it Kennedy's or, yeah, Kennedy's theory. So the M values that is a critical velocity ratio for coarser sand varies as shown, and for finer sand, it also varies as shown. And typical values of C and M for Kennedy's theory, Kennedy's formula are also given. Now, you notice here we have an aspect to do when we are doing critical velocity ratio, we have actual velocity divided by critical velocity. Now, so what this means is that in one way or another, at some point, we have to determine the actual velocity of flow. And what Kennedy used was Kutter's formula, and use Kutter's formula to determine the velocity of flow. When it comes to the water surface slope, Kennedy did not give a relationship for water surface slope, but he assumed that the slope of flow is governed by the available ground slope. Why? Because most of the time, even when you come to design of pipe networks, design of pipes, laying of pipes, normally we try to put them as much as possible to follow a ground profile in order to minimize cost. So he assumed that the canal will be governed, the canal slope longitudinal will be governed by the available ground slope. Now, this single aspect that he did not provide the water surface slope meant it is possible to design any number of channel sections for a given discharge. When you look at Chezy formula, you can only have one velocity for a given slope and a given hydraulic radius. Now, according to Kennedy, when you look at his formula, the general critical velocity formula, there is no mention of slope anywhere. And now that one makes it very complicated. That you can make now many possible designs, of channel cross sections for a given discharge. Because all you need is for you to get velocity, you need bandwidth and a certain height, and you can be able to determine velocity and discharge. So you can change those parameters. If you don't fix the slope, then that means you can have a very large configuration. What we kind of call some kind of equifinality problem, whereby you can have so many cross sections to deliver the same discharge. Now, because of that, solution of Kennedy's design of canals using Kennedy's formula is usually done by trial and error. So you assume a value of depth, solve your problem, finally calculate the slope, calculate the mean velocity using Kutter's formula, and then check, observe. Are the two comparable? If they are not, you repeat the procedure again. Assume a new D, and then you repeat the procedure. We shall see how to do that. And because of this kind of trial and error method, Garrett in 1913 developed what we call Kennedy's diagrams and tried to make exact solutions, explicit solutions of that equation for various for channels with various characteristics. For example, for discharges greater than 335 meters cubed per second, for bed slopes between 1/100 and that, and then for Kutter's N, varying from 0.018 to 0.13. And we shall see those Garrett diagrams, I think, later. Further, we also have a Wood normal data. He tried to correlate, Wood normal tried to correlate bed, I think it is the bed width over D ratio. And once you fix that, then you can easily fix the rest. And so first, let us look at the Garrett's diagram. So if you're given a certain discharge, and where do we get a discharge? If we are designing a canal and we want to determine a discharge, Angela Wanjiku, how would we determine the discharge that we want to deliver? How would we? Angela Wanjiku, Anthony Odima, who can try? Arnold Nadecho, who can try?
Say area times velocity.
It is area times velocity. Now, but it is area times velocity, but remember that velocity and area, the area is what we are designing. The velocity will be associated with our area, but we have to deliver a certain discharge. Why? How do you decide that I'm going to deliver, for example, 4 meters cubed per second? How do you decide? That's a good trial. That's a very good trial. Remember, gross irrigation water requirement, you know you're supposed to deliver so much water. You are supposed to deliver so much depth. You can convert that depth into a volume, and you can also convert it into a discharge if you divide it by the period that you need to deliver the water. So first, when you're designing irrigation systems, even when you're doing the irrigation systems themselves, you have to know the irrigation water requirements gross, so that now you can convert that into volumes and later into discharges. So when you look at this Garrett's diagram, the discharge most of the time will be known. The discharge is most of the time going to be known. You know your rugosity coefficient N. You know your rugosity coefficient N, and the N is varying from which direction to which direction. This table here is for N is equal to 0.0225. This table, whatever here is for 0.0225. And where do we have our B? Where do we have our D? Sorry. Yeah, so something is missing from this. So on the top axis, which is also, on the top axis, we have Y. Y is the depth in millimeters, and then you have slope. You have slope. Slope is horizontal lines. Y are the slanting side. The sloping whatever's, so where the two come to meet, the horizontal and the slanting lines, you get there is some information that is missing, so I should get it, and then we revisit that diagram. So this is one of the Garrett diagrams, and let me come back just to it when we come later after the class, after the break, and we are going to discuss it. Now, the Wood normal design table, you have, if you have a discharge, and you have a B over D ratio, and then if you have a B over D ratio, and either you have B, you can always determine D. And for each B over D ratio, you can select, there's a slope that is associated, and for that slope, you have your mean, your, your critical velocity ratio, critical velocity ratio, and from that you can always get your mean velocity of flow, which is calculated from the Kutter's formula. We have some limitations with, I wonder whether we have other diagrams here. This is the only Garrett diagram. No, the others are Lacey's. And I always confuse reading this Garrett diagram with Lacey's diagram. I've never known why. So we have limitations of the Kennedy's equation, and one of them is that he did not investigate to find out the correct formula for slope applicable directly to the design, causing a very, a big problem. If you choose to solve a problem, you better solve it, so that anyone who is going to come after you doesn't suffer. But when we are designing using Kennedy's theory, you have to, it's like he says, no pain, no gain. You have to suffer a little bit. The trial and error is not good. You have to have a little bit of experience to know, if I selected this value of D, what do I select if it does not agree with my mean velocity of flow? If the critical velocity does not agree with my mean velocity of flow, which do I increase the D or do I decrease it? So you need a little bit of experience to know that. So the Kennedys took Kutter's formula and only adopted N value of 0.225 as average value for channels. The the challenge with that, because we know channel characteristics change from one channel to another based on management conditions, based on natural conditions. So it cannot be constant at 0.0225. He made no attempt to correlate N, the channel, whatever, with channel properties, channel roughness with the critical velocity ratio. And he made no correlation between water surface slope of regime channel and mean velocity or depth. So this issue of not taking care of slope is really like one of the biggest challenges. We have some limitation drawbacks in Kennedy's theory. It does not take into consideration the width or shape of the channel, which have to be assumed. And the importance of the bed width and depth ratio is ignored. But you see, the Wood normal table tried to kind of, both Garrett and Wood normal tried to fix some of these limitations. And especially the Wood normal table tries to work on the B over D ratio. Two, it uses Chase's formula. Why? Because it uses Kutter's. Kutter's is based on Chase's, and so all the limitation of those two have been carried forward, have been adopted by his method. Three, he adopted an arbitrary value of N is equals to 0.0225, and it is not, that one cannot be constant. He aimed at a design of only average regime channel, and he did not specify regime water surface slopes relation. But the Kennedy's diagram show that steeper slopes are required for small channels, and vice versa. Charlene, Jerry, you have a question. He did not consider silt concentration and bed load. And the design of the channel considers trial and error, as the velocity worked out with assumed depth should give the required discharge for the section, at the same time satisfy Kennedy's equation. And finally, the CVR varies according to the silt charge and silt grade, but he did not give a method to measure the value of M or CVR applicable for channels of different silt grades. So according to him, CVR is CVR. and there are typical values in literature for the values of M. For example, for core silt, we have seen is about 1 point something. All of them are about 1, above 1, but the values are different. But in the equation, he stated that it varies according to the silt charge. Silt charge is silt concentration, but only that, according to his notes, according to what we have seen, it only varies according to the soil type, to the silt type. Design procedure, I want to state the design procedure so that when we come, we are going to go to Lacy's theory. And I think I've given either 2 or 3 scenarios when you're given discharge, when you're given rugosity coefficient M, when you're given SVR, and also S. And if you're not given S and you're given the typical, slope of the area, that is the type of the S that you use. So first, you assume a D, then you calculate velocity from Kennedy's equation. Then once you calculate that velocity, you calculate area as Q over V naught. Then from area, you can calculate B by relating area. For example, if you have a trapezium, like this, the cross-section area, you can calculate it in terms of B and D, bed times D, because it is half blah, 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 half the sum of parallel lines plus, or, such kind of a thing. So you calculate the length of this, the length in that, the area will be half blah, 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 and of that. And you can calculate it, therefore, in terms of B and D. Now, if you're not given, this Z here is usually this ratio of your slope, which is provided here. This ratio that is provided here. The horizontal ratio of the slope is usually the Z value in this part. So if you're not given, you always assume 1 into 0.5. Then you calculate the weighted perimeter. Once you have area and weighted perimeter, already you see you have 2 simultaneous equations. So already you can even from here calculate B and D. Then from these two, A and P, you can now calculate hydraulic radius. And that hydraulic radius is used in Chese formula or Kutter's formula. You can even use Manning's, but mostly theory requires that we use Kutter's. But I've seen even using Manning's work. But you use Kutter's formula, calculate for your V, and check the V you have calculated in step 6, the V you calculated in the beginning, the critical mean velocity of Kennedy, how do they compare? Are they the same? Then if they're the same, then you're good to go. Otherwise, if they're not, you have to repeat the procedures again, assume a new value of D and repeat again. So remember here you already have S and so forth. So here I have given a design example which you will follow yourself. It's basically application of those procedures. Secondly, you are given Q, N, M, B over D, but you're not given S. First, you determine A in terms of D. You determine A in terms of D. And remember, this Y still again is the slope. The side slopes of the channel walls, the channel bed, slopes. And then you substitute this equation in Kennedy's form equation and also into the continuity. You substitute this equation and the Kennedy's equation into continuity in order to get discharge. Q is equals to A over V. V according to Kennedy, and then calculate, make D your subject. And if you do, you are going to get this kind of formula. And once you have determined Once you have determined your D, yes, hello, engineer. Now, so determine, once you have calculated that, you determine V from Kennedy's equation, and then finally determine S from Kuta's equation by trial and error. Imagine now going to that very complicated equation and then doing your trial and error. But of course, we have computers that can assist with that. So you assume one value of S, try to solve V. If it does not agree with the other V, assume another new V, a new S, and then so forth and so on. When you're given S, N, M, and B over D, And basically, the idea, and I have tried to indicate the step-by-step procedure. What is most important here is the trial and error component. Now, in case such kind of a problem comes in the exam, I normally ask for a fast trial, not many trials. Otherwise, we'll never finish. Because for you to finish, you really need either a computing device, a high computing device, or you need to be able to program your calculator. And that is one. Then secondly, you will need a lot of time. And then you need experience. You need experience also. I want us to take a break. When we come and look at the Garrett's diagram. And I may take a little bit more time because I need to take care of some work issue still. We may come back at about 8:40 or 8:45. So we will not finish. We will not finish, and I thought we would finish. Anyway, let me then, because I'm seeing I'm going to take some time before I get the kind of information I'm waiting for. Let us look at Lindley formula so that when we come, we just start with Lesis regime. Now, I talked about and briefly introduced a regime channel, but already you see, even with Kennedy's theory, there's very little emphasis on how to come about with that regime. And so Lindley, his innovation came between his and Kennedy's and Lesis. Kennedy's and Lesis, he tried to postulate the core regime now. He tried to postulate the regime concept itself now. By actually providing he tried to postulate, and postulating is kind of to put forward, suggest, advance something. So he now tried to bring out the regime concept a little bit clearly. And according to him, the formula for calculating critical velocity is already here. And he now not only correlates velocity with depth alone, but he correlates it with B. And also a connection between B and D. If you compare these two now, B and D, you'll find that B is equal to that because V here is also equal to V. His definition of a regime channel is that when you have an artificial channel constructed in alluvium to carry silty water, its bed and banks would scour or silt until a depth slope width is attained that has a state of balance, and that is designated as regime channel. Secondly, the regime dimensions depend on discharge, nature of bed, and quality of silt. And three, for a channel to carry a certain discharge and sand charge, it will ultimately develop a cross-section and a slope so that equilibrium is established between the forces acting in its presumed, and it is presumed that the channel can freely develop its regime. So ultimately, according to Lindley, when you have a channel, ultimately you are going to get equilibrium conditions. You're going to have erosion, deposition until you attain equilibrium. It is not widely used, and probably it is because of a number of limitations. And you see, we have even very little emphasis on it. Why it is not very largely used? One, he did not relate to channels in regime. So when he was doing his experiments, he did not go to channels which already had attained regime. So he just went to places where we have straight and regular channel reaches. But that did not mean those ones were in regime. It did not mean the system was in equilibrium. He did not make attempt to correlate rugosity and silt grade. And he assumed a cross-section consisting of a horizontal bed and one, and that ratio of side slopes. And, when you look at natural channels, they are a little bit more steep. They may not be applicable in this case. So when we come back at about 8:45, we will now get to Leslie's regime theory. Then I'm going to take attendance now. And before I take attendance, I have to check whether I want to check whether we are all here. Ama hapa napiga tu piga niko peke yangu. So here we have Arnold, Nandecho, Elvis Karumbi, Evans Kirui, Kwemoy, Bravis, Shalin Jerry. So when we come back, we will start with Lesis. I'm saying we may have to finish it next time. The good thing with design of canals is one of the easiest that we have to do. And I still remember, yes, I'm going to update the tutorials. I will still update the tutorials. So those of us who are not present, it is only Arnold. So let's meet at that time.
I'm present.
So let us look at how to go through the Garrett's diagram. First, you need to have your discharge and your slope. Where do you get your discharge? We've already talked about it. Then you get your slope. Slope, where do you get it from? The longitudinal section. And we have said in Kennedy, you assume ground slope. Then you follow the discharge lines. Where they intersect with the line from the slope. The slope are the horizontal ones. And if they intersect in somewhere where it's not on a line, the horizontal lines, then they intersect on lines which are not the dotted ones, then what do? You can interpolate. So then you draw a vertical line through the intersection point and they will cut across several bedwidth curves. Just give me a minute. I need to check something. Okay. Yeah, so now I said you need slope, you need discharge, and then where the two intersect, let's say, for example, if you are having a slope of 0.2 intersecting with, I want to see somewhere where they intersect precisely on a line. So let's say they intersect at this point. Let me draw here. A slope of 0.15 times 10 raised to power 3. So let's say we have that. So draw vertically. Draw a vertical line that is in 90 degrees. And then, that line is going to cut. It's going to cut when you draw vertically. Through that intersection point, it can be, yeah, let me delete that one. I want to draw, so let's say I'm drawing from here. So that it intersects with the one, this one of 0.5 here. So let me say somewhere here. So you have drawn a straight line. It intersects the slope at 0.15 and the discharge at about 5 at that point. So that vertical line is going to cut. It's going to cut one of these B over D lines. And at the point where it cuts, you can read horizontally V naught on the right side, where the for example, that 0.55, if you draw it horizontally, it is cutting this curve at a B over D ratio of 14.0, and then horizontally you are coming to about a velocity of 0.5 or something, a velocity of 0.5 something, 0.50 something. And then you have a B over D ratio of about 14. Then you choose a pair of bedwidth depth and V naught corresponding to point of intersection obtained above. So you can select one of those two. You can select B over D, a pair of them, two places where they cross. For example, we'll selected that one of 0.15 slope and discharge of 5, and you select another one. Now, notice if you now come to this part here, these slopes of 0.4, 0.3, 0.2 something may not apply. Then you calculate the area channel corresponding to channel bed width and depth. Or then calculate the procedure follows like what we have seen before. Calculate the velocity corresponding to area A. Calculate V over V naught. And this should be equal to 1, or as given by the channel design, or repeat the procedure for other values of bandwidth until the value of V and V naught is the same as given in for the channel design. So the essence of calculating more than one B over D ratios is so that you can be able to ultimately iterate the procedure. So these dotted lines are B over D ratios. And V naught is Kennedy's critical velocity, critical mean velocity. You have discharge, you have slope. I will write that procedure for you. It's usually, I usually always confuse it with Lacy's equation because Lacy also has a number of diagrams, but I'm going to write this one down for you so that because even when the way you have explained, I know without the notes to guide, you will not be able to remember. Okay, so it's already 8:54. Even if we were to start Lacy's, let me see, we are at what page? This is where we are. We are on page 11 and we are supposed to go to 26. We will not finish. So allow me to end at this. We are supposed to go not to 26. 26 should be tutorials. Yeah, we are supposed to come, I think, up to 20. Yeah, we are supposed to come to 24. We won't finish. So we will finish this later this week. And then start with the next. We'll do Lacy's theory when we come back. I know I've not sent these notes and I'm going to send them right away. I'm going to send them right away updated with how to read the Garrett's diagram. I take now my final, I save username and I want to take a poll, a final one. Yes or no, start a poll. See you next week. See you on Friday, sorry.